But I don't count finance. I was like, farmers are right about it. I like these things. And I have one of this for the last year. The other one, that's what yeah, we got used to it. But I was kind of more like secrets. Yeah, I took my test. No. Where was like good damage? Yeah, like my it's like
All right, so let's get started. I hope everyone had a good weekend. So just a couple reminders. Well, one reminder is that your notebooks for the first lab, experiment 1, you'll hand in on Thursday, and you will then use your second notebook to start lab number 2 this week. The other thing I wanted to mention is that I have now posted the first assignment, and there it is on the course website. It's due October 2nd, so there's still a couple weeks before you have to hand it in. I had the due date originally September 30th, which was the Monday, but then I realized that that is the Truth and Reconciliation Day, so there's no classes that day. About the assignment, there's 5 questions that are going to be graded. The first 2 problems are on error analysis, and we haven't talked about that yet. So we're going to start talking about that this week. So if you want to get an early head start on the assignment, you should start with questions 3, 4, and 5, which are like analyzing circuits using standard kind of Kirchhoff junction rule and loop rule type methods. Okay, and then in some cases like combining resistors in parallel and series and that kind of stuff. Okay, good. So what I want to do today is I want to finish off this problem that we started thinking about that was just the series RC circuit. And then what we were going to do is we were going to start with our switch originally in the down position. I will leave it there for a long time, and that's just to ensure that the charge on the capacitor starts at 0 and the current in the circuit is initially 0. So these are going to be our initial conditions, and we're going to need them to complete our solution. It's just like, we have a differential equation, which we have to solve, and the way we're going to solve it is it's going to involve an integral. And you know that when you have an integral equation, if you want to get the final solution, you need to use initial conditions. And so nothing's different here about our differential equation describing the RC circuit. We did some work on this. What we imagined is, okay, we start with no charge, no current, then we flip the switch up at t equals 0. The current starts, and we want to know how does the system evolve from that original initial equilibrium to the new equilibrium. And the way we did that is we said, okay, I can at least get part of the solution by imagining after a long time, this capacitor is going to charge up, and once it's fully charged, the current will go to 0. And so that means dq dt is going to be equal to 0. And so we set that equal to 0, solve for this q, which we called q equilibrium, I believe, and it's just equal to v naught times c. So we did that after the switch has been up for a long time. The system reaches a new equilibrium where the current is 0. And if we put in dq dt is equal to 0 here, we can solve for that equilibrium charge after a long time has gone by. So what we know is that initially at t equals 0, the charge is 0. And a long time later, the charge is constant, C times V naught. And so what we're left with is trying to figure out how to connect those 2 regions of the plot. And to do that, we need to actually solve the differential equation. And so we're going to develop the method to solve that one-dimensional differential equation. So we're going to express. The strategy we're going to follow is to express Q of t, this time dependent charge as we transition from one equilibrium to the next as what I'm going to call QH of t. And I'll tell you why I'm using the H subscript in just a second. Plus a constant Q equilibrium. So this is a constant. We've already discovered that Q equilibrium is going to be equal to C times V naught. And so what we're imagining is that we're going to break this charge into two parts. One part is the part that evolves with time as we go between equilibrium to the two equilibrium states. And then the other part is the constant, the final equilibrium charge we reach after a long time. Okay. All right. So let's see what happens if we do that. So we're going to end up with Q of t is equal to QH of t, which we don't know. We're going to try to find that. Plus this equilibrium value, which we know is C times V naught. And we're going to sub this into our differential equation. And where is it? Let me give this a name. We'll call that equation star. So we're going to take our QH plus CV naught, and wherever we see a Q in here, we're going to replace it with that. Okay, so we're sub into star such that, okay, well, what did we have? We had a V naught over R was equal to a derivative of the charge. Okay, so it's going to be d by dt, it's a time derivative. And instead of Q, we're going to write this QH plus the equilibrium charge that we've already deduced. And then if we go back and look here, we had plus 1 over RC times Q. So that's what we have left. So we have plus 1 over RC times Q. So this is going to be QH plus C V naught. Right? We were guessing that we could write our solution in this way. Yeah.
What's the QH?
We're going to get there in a second. Yeah. So it's like I said, we're sort of guessing, and I think it's a reasonable guess that we're going to have this charge that varies with time. We know that it'll ultimately reach this constant. So this QH is going to tell us the time varying part of that charge. And we'll see in just a second why we're doing this. All right. What is this first term going to be equal to? How could I simplify this first term? We have a time derivative of two terms. One of those is easy to evaluate. Yeah, this is just a constant, right? And so this is going to be d by dt of a constant, which is going to be 0. So all of this is just going to be dqh dt, and that's since CV naught is a constant. Okay, so fair enough. Then what do we have left? We have V naught over R is dqh dt plus, I'm going to separate this into two parts. So we have a 1 over RC QH of t plus, well, let's see, we have a C divided by C, so those will cancel, and we'll get a V naught over R left over. Well, that's quite nice, because now I have a V naught over R on both sides of my equation, and so I could cancel them. And then what we're left with is 0 is equal to dqh dt plus 1 over RC QH of t. Okay, this thing is called a homogeneous first order differential equation. And what homogeneous means is that we have a variable, its first derivative as two terms in our expression, and then it's just equal to 0. There's no constant, or the constant is a 0, whereas the original expression was a variable, its first derivative equal to a non-zero constant. And so our current simplification is that we've made the constant equal to 0, and that's called a homogeneous differential equation. So this is a homogeneous first order differential equation. Okay, and so that means that the left-hand side is 0. And QH of t is called the homogeneous solution. And so the subscript H is for homogeneous. When I wrote Q is QH plus CV naught, just so you know, you don't have to worry about it for our course, but this is called a particular solution. So it's a solution at some known time. In our case, it's a long time after the switch is closed, so it's like t goes to infinity. I know that Q is going to be equal to this value, and that's called the particular solution. Okay, so what we're going to try to do is we're going to try to solve this equation for QH. Once we know QH, then we could put it back into here, and we'll have our final solution for the charge as a function of time. Okay, so let's give this equation a name. We use star, so I'll use number sign. So the goal is to solve number sign, the homogeneous version of the equation for QH of t. Then we will know the capacitor charge at all times since Q, which we really want, is just this QH plus CV naught. Okay, the reason we went through the trouble of forming this homogeneous differential equation where we have the constant as 0 is because this is easy to solve. Okay, and I'm going to try to convince you of that. So let's start by defining tau is equal to RC, and this is going to be our time constant. We don't have to do this, it just makes less writing for us. So then we could say, all right, our homogeneous differential equation is 0 is dQH dt plus, and it was 1 over RC, which I'm going to write just as 1 over tau now, times QH. Okay, so let's work on the solution then. So I'm going to start by taking this term over to the other side. So we'll have a minus 1 over tau QH of t is equal to d QH dt. The next objective is to try to get everything that involves Q on one side and everything that involves T on the other side. So what we'll do is we'll multiply by dt. So both sides we multiply by dt. We'll try to do this slowly in lots of steps. Okay, so we're gonna get minus dt over tau qh of t is equal to dqh of t. So this derivative is like a ratio of a change in QH divided by some small change in time. All right, so then we're gonna divide by QH of t. Okay, so in the first step, we got the time over on the left. Now I want to get QH over on the right-hand side. Okay, so we have minus dt over tau is equal to dqh of t divided by qh of t. All right. Now what we'll do is we'll integrate both sides. So we're going to have the integral of minus dt over tau is equal to the integral of dqh divided by qh. We'll do a little baby step here. The tau is just RC. Those are just constants. Constants we can take outside the integral. I can also take the minus sign outside. So we have minus 1 over tau. The integral of dt is equal to the integral of dqh divided by qh. All right. Now these are easy integrals to evaluate. What's the integral of dt? It's just t. So we have minus t over tau is equal to, what's the integral of 1 over x with respect to x? Ln x. So here, instead of x, we have qh. So this integral is just dqh divided by qh. And so that's the ln of qh. Now we didn't put integration limits in. So that means we get an integration constant. And so I'm just going to put a constant here. I'm going to call it B. I'm not using C because we're using C for capacitance. Yeah.
Assuming function.
What do you mean? What function?
The ln of QH.
Oh, I see. Because we don't want to take the ln of a negative number. Yeah. So when you talk about the charge of a capacitor, you know, you're right. The capacitor has a positive plate and a negative plate. And so what we're imagining is that when you specify how much charge is stored in the capacitor, you usually specify that as just the positive charge of the charge on the positive plate. And then you just know that the other plate has negative that charge. Okay, so this is the integration constant that I was talking about that we're going to need to try to determine, and we're going to use our initial conditions to find that constant. But let's rearrange things first. So what I'll do is, I guess I actually wanted my integration constant on the other side. It doesn't matter. So therefore, we'll have ln of QH t is equal to minus, let's see, t over tau plus some constant b. All right. So if I want to know QH, then what we can do is we can exponentiate. I think something like that. Okay, so E of ln of QH is just going to be QH is equal to E to the minus T over tau plus B. What is the exponential of a sum of terms? How could I rewrite that? Yeah, it's a product of exponentials. That's exactly right. And so that's going to be equal to e to the minus t over tau times e to the minus b. Okay, but b is just a constant. So e to the minus b is just some other constant, right? And so I'm going to define this to just be b prime. And so this is still just a constant. Okay. So therefore, QH is equal to b prime, some constant, times e to the minus t over tau. And so the last thing we have to do is find b prime. So we're going to use our initial condition, which was q, sorry, I have to be a bit careful. So q of t was equal to q of h of t plus c over v naught, right? That's how we defined it if we go way back to the beginning. So there it is. And our initial condition was what? At time t equals 0, this charge had to be 0. So we require q at time t equals 0 equals 0. So therefore 0 is equal to QH of 0 plus C V naught. Okay. But QH at time t equals 0 is just B prime E to the minus T over tau, but T is equal to 0 for our initial condition. And e to the 0 is just 1. And so this is just b prime. So what we'll do is we will go back and say, okay, 0 is equal to QH of 0, which is just b prime, plus CV0. And the only way this could be true is if these two terms are equal but opposite in sign. And so that means b prime is minus CV0. So therefore, b prime is equal to minus c times v0. And we can take that solution for b prime and we'll stick it in right there. And so therefore, QH of t is b prime, which is minus CV0 times e to the minus t over tau. Okay. That means our total charge that we're trying to find is this QH, the homogeneous solution, plus the equilibrium charge, CV naught. But that's minus CV naught, e to the minus t over tau, plus CV naught. Both those terms have the same common factors of CV naught, and so we can pull them out, and we can get our final solution. Q of t is equal to CV naught, 1 minus e to the minus t over tau. And this is the charge on the capacitor at all times after the switch is flipped into the up position. We could check, and it's a good idea to do this check. there's two things we could check. We could check the solution at t equals 0 and the solution at t goes to infinity. So at t equals 0, we needed our capacitor to be uncharged. So if I put in 0 here, I get e to the minus 0, which is 1. 1 minus 1 is 0, and so the charge is 0. So that works. Then we could say, okay, what about a long time later, t goes to infinity, e to the minus infinity is 0. And so then we have 1 minus 0, which is just 1, times CV naught is CV naught. And so that's the final equilibrium charge. And so this has those two limits that we expected it to have. And so that means if we go back and try to finish off our plot, this was T, this was the charge on the capacitor. It had to start here, and then it had to reach the equilibrium value a long time later, which was here. And so this was Q equilibrium was C V naught. And if you plot this carefully over this region, it just smoothly joins these two curves. It starts out kind of linear, and then it has this asymptotic approach to the equilibrium charge. So it looks something like this. I mean, mine, I've drawn it with kind of a kink. There's no kink. It's just a smooth progression approach to that equilibrium charge. There's one important point that we could label on here. And the important point that we're going to consider is when t is equal to tau. So consider the time t is equal to tau, and remember tau is just RC. So we can pick whichever values you want. In fact, you're gonna study the circuit in lab 3. So lab number 3, you'll study exactly this circuit. Okay, so all we have to do is see what happens if I set t equals to tau in our solution. So Q, when t is equal to tau, is CV naught, and then it's 1 minus e to the minus, there's t over tau, but we're saying t is equal to tau, so tau over tau. And so that's clearly just CV naught, 1 minus 1 over e. What's e? What's the value of e? Yeah, it's 2.7. Let's call it 3, just to make it simple for a second. So this is 1 minus a third, so that's 2/3. So basically, after one time constant, the capacitor has reached about 2/3 of its final charge. Okay. If you put in the correct numbers, I think I wrote down, let's see, did I write down the value? Yes. So it's not 1/3. 1/3 would be like 67%. It turns out to be more like 63%. Okay, so the capacitor reaches 63% of its final charge after one time constant. So on our plot, if we wanted to add that point to our plot, we would find about 63%, I don't know, somewhere around here. So this would be like 0.632 of CV naught, and that time corresponds to one time constant. That's useful information because if you want to fully charge a capacitor using an RC circuit and a battery, which is exactly the situation we're considering here, the time it takes to fully charge is several time constants. So it's typically 3 to 5 time constants you have to wait for your capacitor to fully charge up. And so if your R and C combine to be like a microsecond, then when you close the switch, you wait 3 to 5 microseconds, and then you could be sure that your capacitor is basically close to fully charged. Yeah.
How long does it linearly grow? I know it's not actually, but roughly linearly grow before it kind of starts.
Oh, yeah, so this is, okay, so this is a bit of an aside. I don't know if you've done, did you do Fourier, sorry, not Fourier, did you do Taylor series already in some math class? Yeah, okay, so the Taylor series for an exponential, e to the x, okay, you know Taylor series, what is it? Well, how do you write the exponential as a series? So it's this kind of thing, right? And so you can see that when x is small, say x is 0.01 or something like that. So that would mean x squared is 1 times 10 to the minus 4. And so that's going to be really small. And x cubed is going to be 1 times 10 to the minus 6. That's going to be very, very small. So for small values of x, you can throw away all of the high powers of x and basically just consider the first couple of terms. And so there you can see it's linear. So e to the x is 1 plus x. That's a straight line with an intercept of 1, right? So your question is, how linear is it? Well, I can't give you a definite answer, but it's basically until this x squared term starts to become appreciable. And so for us, we have e to the minus t over tau. And so that means we're going to get 1 minus t over tau. And then it's going to be plus 1 over 2 factorial t over tau squared. And then it'll be minus 1 over 3 factorial t over tau cubed, and plus and so on. And so if these are small compared to t over tau, then we get that linear behavior. Yeah. And so the answer to your question is, how much of a deviation from linearity are you willing to accept? So, all right, good. Any other questions about this? Probably in a future assignment, I'll get you to go through this kind of procedure. It's similar to what we've done here, but instead of an RC circuit, it'll be a circuit with maybe a resistor and an inductor or something like that. Okay, let's do one other thing before we leave this, and that is, we now know the charge on the capacitor, but usually when we do circuit analysis, you know, we might be more interested in, like, what's easier to measure in the lab is not the charge on the capacitor necessarily, but the current in a circuit, for example. So to find the time dependence of the current, what we would do is we would evaluate I of t is going to be dq dt, which is going to be d by dt of what? Well, it's cv0 1 minus e to the minus t over tau. Okay. What's the derivative of the first term going to be? 0. Okay, and so that's going to be, let's see, 0. And then we'll pick up a minus sign here, so we'll have minus d by dt of e to the minus t over tau. What's the derivative of the exponential going to be?
-1 over tau times squared.
Yeah, minus 1 over tau times e to the minus t over tau. So you get the exponential back again. And so this minus sign is going to cancel with that minus sign. And so I forgot something. What did I forget? Sorry, maybe somebody said it, I didn't hear it. What did I leave out here? Yeah, CV naught, right? So CV naught multiplies this exponential. So it's a constant, so it doesn't affect the derivative, but I still need that constant in there. Okay, good. So now the minus signs will cancel. Tau is equal to RC, and so the current in our circuit then is equal to CV naught divided by tau, which is 1 over RC, e to the minus t over tau. And the C's are going to cancel. And so our current is equal to V naught over R, e to the minus t over tau. We can kind of just mentally check the two extreme cases, t equals 0 and t goes to infinity, and just see if they make some physical sense to us. Let's start with t goes to infinity. We get e to the minus infinity, which is 0. And so the current will go to 0 a long time after the switch is closed. That makes sense because the system's finished evolving to its new equilibrium. The capacitor gets fully charged and the current goes to 0. At t equals 0, we're going to get e to the 0, which is 1. And so we'll have V naught over R. And so let's go look back at our original circuit here. And let's just think about what happens when we close the switch. So we flip the switch up here. The capacitor's uncharged initially. So at t equals 0, if we did the voltage loop rule, we would gain the voltage of the battery. We'd lose some voltage across the resistor, but then nothing happens at the capacitor. It's uncharged. And so there's no voltage across it. So nothing happens here. So we just get V naught minus IR. And if we solve for the current, we get V naught over R. And that's exactly what our solution for the current tells us. That if I put in t equals 0, I'm going to get just V naught over R initially. So initially you close the switch or you flip it up. It's like the capacitor's not there. But then as it charges up, you start to develop a voltage across that capacitor. That means the current through the resistor has to decrease with time. And there's the exponential decrease. So if this is time, this is the current, then at t equals 0, we sit right there at V naught over R. At t goes to infinity, we have to be at 0, and it's this exponential decay of the current. Again, we could look at the current when t is equal to tau. We're going to get e to the minus 1 at that time. And so we get V naught divided by R times e to the minus 1. Again, e to the minus 1 is, it's about a third. I guess it's a little bit bigger than a third. And so maybe it sits somewhere around here. And so here is 1 time constant. And the current drops to, maybe 35% of its maximum value or something like that. This is supposed to be a straight line. And so this is going to be V naught over R times 1 over E. Okay, good. Any questions about this? All right. So how are we doing time-wise? Okay, so we have about 10 minutes left. And so what we'll do is we'll start our little discussion of uncertainties. I'm gonna move this over here. And then we can do our new topic here. So this is going to be uncertainties and propagation of errors. The reason we're doing this is just because this is a lab course. You're going to be collecting data. You didn't do a ton of data collection in lab 1, but starting from lab 2 going forward, we will generally be collecting and analyzing data. And so every single measurement you make is going to have some associated uncertainty. And then we often will take those measured quantities and then calculate new quantities from them. And those new calculated quantities are going to have some uncertainty because they were generated using uncertain measurements. And so we want to know, how does that uncertainty propagate from the original measurement into some calculated quantity? Of course, you've done this in first year labs already. What we're going to find is that a lot of what you did in the first year labs will translate over, but there are some differences. And so I want to highlight those differences. Okay, so every quantity that is measured has an associated uncertainty. That uncertainty will never go to 0, right? You could argue that, if you made a measurement using crappy equipment, maybe the uncertainty would be larger. And so you go and you go buy the best equipment that you possibly can, so you can reduce the uncertainty in your measured values, but it's never going to vanish completely. Okay. So I just want to think of a simple example. So the experiment that I want to think of it is really simple. I just want you to imagine that you go to the top of a tall building and you're just going to drop a penny, or you can't get a penny these days, a nickel, and you're going to time how long it takes to hit the ground. Okay, so we drop a penny from a tall building and measure the time for it to reach the ground. So we're going to make a table of repeated trials. And so if you were actually to do this, maybe you're at the top of the building and your friend's down on the ground, you're talking on your cell phones, and you say, okay, I'm gonna go 3, 2, 1, and when I say 0, I'm gonna release the penny. That's when you start your timer, and when you hear the coin hit the ground, you stop your timer, and then we'll record that time. And then you do the measurements, and every time you do a trial, you're gonna get a slightly different result. And so would be 1, 2, 3, 4, up to n trials or something like that. And so maybe the first trial you record, 148.25 seconds. And then the next one you get 151.36, and then you get 146.20, and then you get, 153.67, and so on, 149.7. 1 or something like that. Okay, so I just want to think of, what are some reasons that all of these measurements turn out to be a little bit different? Just give me anything you can think of. Error. Yeah, human error is, so never write human error in your notebook. So that to me is almost a meaningless statement. So I want us to really think specifically about what's actually going on. Human error is just like a throwaway comment that says, you know, we're not perfect, so we don't make perfect measurements. But what's not perfect about it? So what about the human interaction with this experiment is causing the numbers to be different each trial? Yeah, reaction time is reasonable. Okay, so I'm gonna go 3, 2, 1, 0, and I drop the penny. And so the moment that I drop the penny after saying 0 might change every trial a little bit. There's also the person on the ground who has to start the stopwatch, and then they have to stop it when they hear the coin hit. And so there's 3 different kind of reaction times that might vary from trial to trial. Okay. What else could happen? Sorry, there are 2 things. Wind? Okay, yeah, that's right. So if there's a crosswind, then as the penny falls, maybe it's getting blown off to the side, and that wind might be a little bit different each time you drop it. There was something else. Did someone else say? Oh, it's the same? Okay. So there's also a drag force, and so that drag force will be different if the penny drops vertically, so its plane is in the vertical plane, or if it's falling flat, or if it's tumbling. And so how the coin tumbles as it falls might vary the drag. The temperature could be changing during the day. That'll change the density of the air. So hotter air will be less dense and there'll be less drag as the penny falls down. There's really 2 different kinds of uncertainty that we're talking about here. The reaction time would be sort of a random error. So you'd think that you're going to have an average reaction time. Sometimes you're a little slower, sometimes you're a little faster. So that's some random uncertainty. The temperature effect, in principle, we could account for that by saying, all right, I'm going to measure the temperature of each trial, and I'm going to know how that affects the drag force, and I can make small corrections. That's more like a systematic uncertainty where if you were really detailed about your measurement, you can make corrections for those sorts of effects. Okay, but anyways, let's imagine that we've done a careful experiment. Like, we could also, how could we improve our measurements so that the fluctuations from trial to trial go down? Yeah.
Replace the 2 people with electronics and machines.
Yeah, so you might have like a little laser beam and a photodetector, and when the coin crosses that beam, it starts a stopwatch, and when it crosses a beam on the ground, it stops it or something like that. So you could get more sophisticated so that the randomness or the variation from trial to trial goes down, but it won't vanish completely. Okay, so how are we doing in time? 3 minutes. So what I'm going to do is I'm going to draw a histogram of what these data might look like, and then that's where we'll stop for today. So we're going to plot a histogram of the N trials. And so what that means is we'll have a horizontal axis, which is going to be like the fall time. And then what we're going to do is we're going to break that fall time into bins. And so there'll be one bin that's this wide, and then beside it, we'll just have all these different bins. And so maybe the bin width is like half a second or something. So the first bin might correspond to, I don't know, 148 to 148.5. The second bin would be 148.5 to 149, and then 149 to 149.5, and so on. And all we're going to do is we're going to count the number of trials that land in each of these bins. And so this would be the number of occurrences or something like that. So the number of times one of our trials falls into each of these bins. If we have a bin out here at really low fall times, there might be only 1 or 2 trials that land in that bin. And so we get something like that. And as we get to longer and longer times, we're gonna get more and more trials falling in these bins. There'll be some variation, it's not gonna be perfect, but then the bins will start getting taller, and there'll be one that's at the peak. And then we're gonna have these ones where they're at higher than average times. And so, you know, out here it might be like 155 or something. And again, we're not gonna get a lot of trials in those extreme bins. But then they'll start building back up. And so maybe our histogram looks something like that. If you had your data, where would you expect, how could I come up with some kind of quantity from these data that's going to locate where the peak of this is? Take an average, right? So if I take the average of these measurements, so I'm going to add up all the different fall times for I equals 1 to n, and then I'm going to divide by n. That would be the mean value, and the mean should sit right in the center. The distribution, if your uncertainties are really random, your distribution should be symmetric, and the mean should sit at the peak. What else can I use to try to characterize the shape of this distribution? This is the last thing we'll do. Yeah, a Gaussian curve. So this would follow some, we could put a smooth curve on this, and in the limit that we did an infinite number of trials, our data should follow that smooth distribution. So we have a peak in our distribution. We also have a width. How do I characterize the width? Standard deviation, right? So I didn't draw this perfectly. My peak should sit where the red line is. So standard deviation characterizes how wide this distribution is. And so here would be something like mu plus a standard deviation. And over here would be something like mu minus a standard deviation. Okay, that's where I'll leave it. Next time, we'll write down the standard deviation, and then we'll talk about what we expect for the behavior of these data as we take more and more and more trials. Okay, good. Thank you very much. We will see you on Wednesday.
Do we need any special for our lab notebook?
Structure. What do you mean by structure?
Like I did the report of what we did about